All right, good morning, good afternoon, good evening, everybody. Welcome to another edition of TridiumTalk Developer Series. Today we'll be discussing the JSON Toolkit, and we'll be joined by Jason Woolard and Nick Dodd, some software engineers and developers of the JSON Toolkit. I am Mike Smith, product manager with Tridium, and a couple of quick things before we get started. Just recently, in this month, we surpassed 1 million installs of the Niagara framework. So big shout out to all of our developers and engineers and Niagara community who made that possible. So very excited about that. Niagara 4.10 now available. And hopefully you all have had a chance to contact your support channels and download and install and start using Niagara 4.10. Got some exciting new features and functionality in that. And we are just around the corner from releasing Niagara 4.11. We are currently in early access testing. Beta testing will be coming up soon. If anybody on the line is interested in becoming an early access participant or a beta participant, please reach out to the email address on the screen and we will get you set up. So very excited about some of the new enhancements in Niagara 4.11. Very excited about the Ubuntu desktop and server support, adding that to the OS, TLS 1.3 and BACnet Secure Connect. So again, if anybody's interested in testing any of these new features, please reach out and we'll get you started on that. A couple quick housekeeping items. If you have questions throughout the presentation, please feel free to enter those in the chat. We will answer those as they come up, and we will, if there's anything for Nick or Jason specifically, we'll save those for the end. All right, without further ado, I'll turn it over to Nick and Jason to get us going here and overview the JSON Toolkit.
Thanks, Mike. So, as you can see, we've used a JSON encoded title slide in order to remind you what we're talking about. And that is a lightweight data encoding consisting of key value pairs with the key on the left and the value on the right, structured within arrays and objects using square and curly brackets, with typing including Boolean, numeric, and strings, much like the framework. The JSON Toolkit was added to Niagara in 4.9 and allows you to create JSON strings using schema components to map from the rich object model of the framework into a payload that you define to suit your application. It also enables parsing of incoming payloads or messages using components described as routers, selectors, or handlers, which we will explore later. It's important to note that the toolkit is transport agnostic. We don't stipulate the protocol that you will use to send or receive messages, although it is commonly used with MQTT or HTTP.
Hey, Jason, sorry to interrupt. Can you share your screen, please? Are you sharing your, yep.
Is it not working? Sorry.
No worries.
I
think, there we go.
You see it now? Okay.
Yeah, good.
The title slide was JSON encoded, illustrating the Boolean, numeric, and string data. And this is the overview with the transports, just for the audience's benefit. So those transports are often key to cloud-based applications, but there are also use cases such as feeding data into libraries or exporting to a file or database, which can take place local to the station. Also of interest is the fact that you can use the toolkit to write primitive drivers for devices which consume a JSON payload. For example, many smart home devices like lights support this approach. Some features that support these use cases are bindings. So when the schema is bound to a point, it updates on change of value. Queries, which allow the result of any equal or nequal query to be embedded in the output. So perhaps history data, or indeed any BI table could be used. And support for the semantic model of Niagara via tags and facets, allowing us to apply meaning to the messages that we're creating. Alarming is supported by means of a JSON alarm recipient, similar to those used for drivers like BACnet or SNMP, but in this case, you can define which properties of the alarm record are used, with SMS via a cloud service being an obvious use case, or even acknowledging alarms with voice or image recognition if you feel inclined.
Thank you, Jason. So now we're going to learn the basics of a JSON schema in under 2 minutes. So we have a wind speed numeric writable updating every second, and we've added a new JSON schema to our station. So you'll notice this large text field here, which is the output slot, which will in a short while contain our formatted JSON output. Now the first thing we need to do is define our format for the JSON underneath the schema. So I've dragged in an empty JSON schema object, which will be our opening and closing curly brackets for the rest of the message. Now we've added a current time property from the palette, which will hold the current time as a key value pair and give each message some uniqueness. And we've nested that within the root object. So now to include some station data, we're going to add a JSON schema bound object. So the bound object is similar to a binding that you might find on a PX page in that it's bound to a specific slot within our live station. So I'm going to go ahead and select our numeric writable, and if you remember, it's updating every second. This is relevant because the JSON schema will subscribe to its bindings, and as you can see now, we're getting a new JSON string every time that downstream point updates. Now the object here is called sensor data because that's the name that I gave to my bound object underneath the schema. But amongst other options, I can change this to instead be the name of the target point. And I can also get rid of all of those in slots if I don't need to see them by switching to just the summary slots as you would see on a Wiresheet glyph. And the takeaway thing to learn here is that we're essentially modeling our JSON format by nesting objects and components underneath a JSON schema and then hitting the generate action to create output.
So we've just seen a binding cause JSON updates on change of value. But while I'm sure you can imagine cases where absolute odds work, it really doesn't scale well if you end up with a schema per point. To overcome this, we have the relative JSON schema. Just like with reusable PX graphics, you use relative odds, as shown here in the binding. Obviously, a relative odd needs to be resolved against a base object to achieve something useful, and that's where the base query comes in. Using this, you locate components to export using equal or equal queries. This could be for each device, points in override, points with a certain tag, and in COV mode, when the schema is fed base items, it subscribes to the resolved components in order to generate output when any included property changes. So if you have the out slot included and it changes, then you get a suitable payload for that point generated, as you can see. A nice side effect of this is that newly added devices or points can be automatically included in your exports. And further still, you can move points between schema to increase verbosity, for example. Inbound processing is split between 3 categories. Routers, which determine where all or part of the message should be passed next. Selectors, which further dissect JSON messages. And finally, handlers, which do something based on the message. We have a set point change and alarm acknowledgement handler at present, and we assume you guys may be creating more of these as needed. We've tried to keep functionality in small, simple components which can be chained together.
So now we'll start off by looking at some examples of these inbound importing components. We're going to begin with the JSON message router. you'll notice that there is a slot here called key, to which we have the value message type. And this matches one of the fields of our example JSON message that we have here on screen. Note that for this message, it's a registration message type. And so the message router has routed that entire message to the registration slot. So then it can be passed to downstream components which will further process the message. One such component that could do this is the JSON demux router, whose purpose is to demux all the top level key value pairs of a JSON message into slots. And you could chain multiples of these together if you had nested objects within a JSON message. But for ultimate flexibility, we have the JSON path selector. This allows you to specify an XPath-like query expression for selecting things within that JSON message. This could be values that are nested several levels down or within arrays. It could be the nth entry of an array, or you could specify more complex conditionals such as these here. Now, when we created the JSON schemas, one of the key aims was to help non-developers create formatted JSON strings to represent station data. But we think that JSON schemas do a lot of the heavy lifting, such as creating bindings, managing subscriptions, and multi-threading, that can be quite complementary to a developer's code and save them some time. So we're going to look at how you might create JSON schemas as a developer. And for this task, we've set ourselves the requirement: can we create a JSON schema to publish BACnet device and point data in a JSON format? This is our decided upon format. We have a JSON object, and then we have an API string, which is a numeric property. Then we'll have a timestamp to give each instance of the message a bit of uniqueness. Then a new object for the BACnet device config. And finally, at the bottom, we have an array to contain all the different live data for BACnet points underneath that device. So we're going to begin by defining the slot path to our favorite BACnet device. On the second line, we've defined a BQL query for extracting the required pieces of each BACnet point which we want to show in our JSON string. So we've gone for the name, the object ID, and the current status and value. Now we introduce the JSON Schema Builder class, which is very much based on the conventional Java builder pattern, because you'll notice the last part of this line is a build method which returns the JSON schema, which you can then mount into a running station. The first thing we've done is we've given it the BQL query, which we defined on the second line. Next, we must define the format that we require for our message. So once again, we begin with a root object, which is your opening and closing curly brackets. Then we add a fixed numeric property, which is the hard-coded API version, which of course could be linked to something in your station if that could be variable at a later date. And then we have the current time property, as we saw before. Next, we add a new fixed object called config, which will hold our BACnet device configuration. We have two bindings within this, one which is just a bound property because it's a single value, the address of the BACnet device, and a bound object for the device object, which will contain a list of multiple values. And you'll notice that we have step down and step up there because we are nesting one level down within the config object. Then finally, it's time to inject into the JSON string our live BACnet point data. And we're using a bound query result for this, referencing our query that we identified earlier. Now you'll notice that the last parameter is a query output style. And we've gone here for an objects array, which we'll see in action shortly. So the result of running that code and then mounting it in a live station is this JSON schema. you'll notice that the query ORD has been populated and it found 2 BACnet points underneath this device. So when we run the generate action, this string is what was generated. So we have our version and timestamp headers at the top. Then our config object with the BACnet address as a property and the device settings object with many different properties. And then finally, we have our snapshot of the latest BACnet point data for our 2 points that we found. And you'll notice there's 4 key value pairs per object because we had 4 columns in our BQL query. And I mentioned that we had an objects array style because essentially here we have an array of objects, 1 per row in the query results.
So we've seen a schema being built, but what if we want to override its default behaviors? There are many options for this in the docs, but let's focus on the most accessible. First, we have the inline writer, which allows you to do what you like with the JSON writer used inside the schema. For example, nest objects, use conditionals, iterate through the station, subscribe, or aggregate values, and so on. And secondly, the type override allows for customization in how the schema maps Baha types to JSON. For example, a Niagara B status of OK might need to be operational in a given protocol, or perhaps some logic will decide. So let's look at this in practice with a charting example. Other libraries are available and subscription via Baha script is not covered in this session. We start by building a schema to feed our chosen library. Fixed properties can be used to configure how the chart looks, and either bindings or a query could be used to locate the data. Here, the result of a BQL query in the blue box is included via the query result in the green box, which following the selected output style will yield the data shown on the right. Inserted into our charting library, this works as is. But what if we want more? For example, to allow the user to easily change colors in the chart. For this, we could use the inline JSON writer, adding a bcolor property, which attracts its field editor, and then some simple code to output a key with our colors hex code, which could also be done from your own module rather than the program object we're using here. So let's see our new schema and its properties in use. First, we demonstrate the binding. Changing a point's value causes the chart to change. Then we use our new inline writer to inject the chosen color. And voila. Now, if you note the units facet shown in the tooltip, you can see a type override being used to alter the display of the units.
So another area we're going to look at now in terms of extending the toolkit are those query result styles, which we saw earlier with the objects array. If you'll recall that example, we had a JSON schema that created a JSON formatted string for BACnet device and point data. And the point data was the bit which we queried. But a query result is essentially a 2D array or table of data. Now, there's many ways to slice up such a data structure into curly and square brackets to represent objects and arrays. And we have made our best attempt at representing the most common formats you might see in the real world that come for free with the JSON Toolkit. But of course, there's going to be many different variations in the real world and complex requirements. And so we needed to give developers a way of defining their own styles. Now, anyone in the meeting with a grey hair or three with experience of Linux in their past may have come across the command line utility Calce. Its purpose is to simply parrot back to you any text that you pipe into it in a triumph of ASCII art. And we thought it might be a little bit more interesting for our example today to see, could we actually make Calce report our live backnet data at the commands line? So all the developer needs to do is extend bQuery result writer to define their own query output styles. To make it appear as an option in the drop-down list in Workbench, then all you need to do is make that same class an agent on JSON schema bound query result, sorry. Then all you need to do is implement the method Append JSON, which is passed two useful objects as parameters. The first of these is the JSON writer, which is the current JSON writer being used by the JSON schema to create the JSON string. And you can append anything you wish to this in terms of adding new objects, arrays, and key value pairs. The second parameter is the query result holder, which is a cached value of the execution of your query, be it BQuery or NQuery, etc. And I would advise being careful at this point when you do define your BQuery queries or NQuery, for example, in a JSON schema, because you don't want to query the entire station and cache it all in memory. And also the generation of huge long strings, if you've got tens of thousands of points, could be a little bit costly for the JVM. And so looking at the query result holder in more detail, it has two methods you will need to use. The second of these is quite self-explanatory. It gives you a list of the column names. The first of these returns a list where each list entry represents a row of the query result table. And then each entry in the map in that row represents each column's worth of data. So here's our lovely implementation. You can see that we've begun by adding a new JSON object, and always be sure to end an object or close an array in a finally block, just in case of any runtime errors which might cause some formatting issues by missing out on that end object. Next, we've drawn our ASCII art by various key value pairs. And finally, we've written a couple of helper methods to write our backnet data into the speech bubble. So the first of these is using that get column names method to just create a CSV list of the column names. And then we're using get result list to iterate over each row in the table. And for each one, we're creating a new JSON array. And then within that JSON array, we're iterating over each column value, and we're using the toJSON type helper methods to convert it from a Baha type into a JSON primitive. So this is the backnet example that we saw earlier. All that we've done here is we've changed the query output style to Calce JSON. But hang on, there's something still missing here. Jason, how are we going to get this available at the command line?
So implementing a bExporter let us create JSON files, should you have a machine learning or similar requirement. So we went ahead and added that exporter. But the framework often gives us features for free. And in this case, it's web access to the schema output. So without creating an additional servlet, you have HTTP access to the payload, as Nick will now demonstrate.
So all that's left to do is to use curl to hit that exporter's URL on the schema and enter our station credentials. And there we have it, requirement fulfilled. So if you overlook the sort of slightly eccentric nature of the example we chose today, I hope you can see that we now have station data in a nice, parsable and machine consumable format, and we got it to the command line. And I suppose the takeaway is that we had a quite complex bespoke requirement for the converting the station data into a quite strange JSON string, and we were able to do that with relatively not too much code. And I guess that's an odd sales pitch to a call that is primarily developers, but I'm sure you agree that with the JSON schema, hopefully it can take care of some of that heavy lifting within the framework, which will free you up to use these JSON strings for more interesting things like using MQTT brokers or sending the messages to cloud brokers. And yes, this slide is not lying. We did our extra mile and created developer documentation on top of the regular Baha docs. And there's various examples of extending the toolkit in there, including the Calce example you saw today. And we tackled our developer kryptonite and wrote some UML graphs, which I hope you find useful for explaining the internals of the toolkit and how it works.
So to conclude, the toolkit is available from 4.9 onwards and available in your demo licenses. We also encourage you to review the Niagara Pro Tips on YouTube or the free e-learning course available via Tridium University. Thank you for your time, and we hope you found the session useful.
Great, thanks, Nick and Jason. There are a couple of questions we would like to answer live.
Yeah, so Nick and Jason, you've got some great documentation there. Are some of these station examples you gave in that documentation, or would it be best to reach out through your sales support channel to get the Wiresheet layouts that you presented in your presentation?
So the JSON Toolkit module itself has an examples folder, which has some examples that help people to get started with building particular payloads. And some of the code that we've presented is already in the documentation. If there's a specific example that someone's seen that they want, by all means, contact your support channel and we'll see if we can make that available to you.
Great. All right, this one is a two-parter about the bound query specifically. This user has an example where they are collecting a lot of Modbus meter data, doing some processing with it, and need to publish it over MQTT and need to send it every second. Would that mean that the bound query is triggered, or does that mean that using a bound query and triggering that every second is the way to go, or might there be a better option?
I don't think it's probably the best way. I would say if it's every second that you don't want to use the schema in change of value mode, but instead on-demand mode, and then use a trigger linked to the generate action on the schema. So the query result would be cached and then retrieved at the point the schema is generated. So with a 1 second interval, you've likely got some competition there between query execution and generation. So I would suggest using a trigger linked to the generate action with the interval that you require.
And with that bound query, if we're publishing a large amount of data, is there any way to slice that data up before publishing it?
That kind of pagination would be achieved using BQL. So if you want to put constraints on the query, that's done in the query itself. Or alternatively, with the inline JSON writer, you could put conditionals in to suit your application. So you've got absolute freedom there as a developer to do as you wish, whereas the end user would be using BQL to limit the scope of the query, for example.
Okay, I think those will be helpful solutions. Next question. Can I turn the whole station into a generic schema and then use that HTTP access provided as a REST API for all of Niagara?
Yes, you can certainly link the JSON schema up to a HTTP transport if that's what you would like to do. In terms of turning the whole station into a generic schema, I think that's where the relative schema that we touched on towards the beginning of the presentation comes into play, in that you can have a message format that contains just that point's worth of data, and you could subscribe to many points. If you want to include many points in a single JSON message, then the actual queries is probably the better way to go, but it comes with that caveat again of, yeah, you don't want to be querying an entire station, especially if it's a very large station with, you know, many thousand points. Yeah, I hope that
Right,
answers
so
the question.
certainly you could do that, but you just want to be careful about how and when you do that.
Sure, yeah.
Yeah, and you might find an alternative such as Obix is more appropriate in terms of having path-based access to specific areas of the station, where, you know, a schema for the whole station or multiple schema would become quite an engineering endeavor, depending on the complexity of that station.
All right, finally, we have 2 questions about licensing. I know that these may be more appropriate for a sales channel, but perhaps you may have some insight. First of all, is this JSON Toolkit feature licensed?
Yes, it is. In terms of a engineer's comment, I would say the intention is that the pricing is very reasonable in relation to other drivers. It's not meant to be a huge barrier to entry, but yes, it is a licensed component of Niagara.
And is that based on the SMA?
Yes, the JSON Toolkit requires active SMA in order to continue functioning.
So if that SMA expires, then what happens to the customer station?
Nothing to the station as such, but the JSON Toolkit will cease functioning on the next reboot of that station. There are tools in the JSON schema service to generate an alarm in advance of that happening. And the station itself also has a warning on the web logon screen. But at this moment in time, the JSON Toolkit is linked to active SMA.
Okay, thank you so much for those answers. Hopefully we clarified things for people. Oh, one more question just popped in. Is there a way to have histories send a group of data in one message? So combining the data from a number of histories and putting it into a single message.
Yeah, absolutely, just with multiple queries. In fact, using those queries, because it can be any BI table, you could either have multiple history queries and inject those into your schema, or you could use the series transform output with the ORD scheme related to that pre-existing feature. You can even mix and match live station data with an alarm record and say the last 5 history records for that. So you can be quite creative in how you mix and match from the different spaces in Niagara to form a message that suits your application.
And that looks like all the questions we have for now. Certainly, if there are more questions as you think about them over the coming days, please feel free to email us and we will get back to you. And I'm going to hand it back over to Michael Smith to wrap things up.
Great, thanks, Blake. Thanks again, Jason and Nick, for the awesome content and coverage today. So I just want to highlight a few additional Niagara resources and some content. As always, check out Tridium University. There are a number of great free courses on there. And you can find more of our Tridium talks on the Tridium website. Just go to Tridium and look for the events page where you can find previously recorded Tridium talks as well as output of the Q&A sessions as well. And check out the Niagara Pro Tips on our YouTube channel. And thanks again, everybody, for joining today. Thanks again, Nick and Jason, and we'll catch you guys at the next Tridium talk.